It is my pleasure to introduce our next speaker, NVIDIA's CEO, Jensen Huang, joining us on screen for a conversation moderated by David Lin, Senior Director for Platforms at SCSP.
Hello, everyone. It's a marathon, not a sprint, so keep that in mind. Today, we have the privilege of hearing from someone at the center of the AI revolution, Jensen Huang, the CEO of NVIDIA. NVIDIA, as I'm sure everyone in this room knows, is a full-stack tech company that is really paving the way for global tech innovation. We wanted to invite Jensen to speak about the future of AI and technology and how it will transform all aspects of our lives. And so with that, Jensen, welcome to SCSP's Global Emerging Tech Summit.
Thank you. I wish I were there in person. Happy to support this important work.
We're super excited to have you, and thanks again for taking the time. So let's get started. Jensen, we've had a long day so far. We've been hearing from a range of industry, government, thought leaders who have been offering their perspectives and their visions on the future of geopolitics, the future of national security, the future of technology policy. You've spoken about the importance of having perspective as opposed to vision. What was your perspective in 1993 when you founded NVIDIA, and how's that changed or stayed the same 30 years later to today?
We founded the company at the beginning of the microprocessor revolution. Silicon Valley was buzzing with what CPUs could do, what microprocessors could do, and just about every single company was focused on building microprocessor systems. And we believed that there were applications problems that general purpose computing don't solve very efficiently. But that if we added a specialized type of processor, a throughput-oriented parallel processing system that doesn't run everything, but can accelerate certain functions within an application extraordinarily, orders of magnitude faster, 1,000 times faster, 100 times faster, that there are certain types of applications we could make possible, that we could democratize these types of applications and make it more available to people. And we called it accelerated computing. And 30 years later, it is true that CPUs no longer scale very easily. And we can no longer, because of the applications that we are running today, we can no longer afford to just use brute force CPU scaling. And so as a result, we find ourselves at the center of two fundamental computing transitions. One towards accelerated computing, because we need the order of magnitude reduction in cost and power, while we need that orders of magnitude increase in scale to solve some interesting problems. You know, of course, the early problems that we solved were really, really quite terrific to me personally. Molecular dynamics, the ability to do CT reconstruction with ultra low dose X-rays, seismic processing, image processing, and all of those types of applications. And then about 13 years ago or so, 14 years ago, we started to see the beginnings of what is now called deep learning, what people all understand to be deep learning. And we saw a whole new way of doing software. And what I was excited about was enabling this universal function approximator, where you give this piece of software a whole bunch of examples, and it doesn't really matter how big the data is and how much dimensionality is in the data, that with large enough computers, you could learn the function from the examples, and otherwise known as machine learning. And we were fortunate to realize several things, that this isn't just some computer vision miracle that happened, but this is a whole new fundamental way of doing software. Remember, AI is not a widget, AI is software. And it's a new way of doing software. And then the second thing that we realized, and that transformed the company in the last decade or so, is that AI is not a chip problem, that AI is a systems problem. because the amount of data that you want to train with and the amount of the size of the models you want to train with are so large that you really have to rethink how computing is done and how accelerated computing was done altogether. And we transformed ourselves into a systems company. And today we're a data center scale company. Almost everything that we do includes processors and networking and software and switches and silicon photonics and all of this incredible technology that what makes large data centers today. And so I think that perspective of wanting to solve problems that normal computers can't led us to today, and that mission statement, if you will, that sense of purpose for solving those type of problems remain at the company today.
That's a great segue to our next question, which is that as again the room knows, NVIDIA graphics processing units are really fueling today's momentum behind generative AI. SCSP just published a series of memos on generative AI. And in the report, we talk about how Gen AI is changing the very nature of the kinds of innovation you're making reference to. You've described NVIDIA as the engine of AI and characterized Gen AI as unlocking the production of intelligence. What's the implication of all of this? What are some of the Gen AI applications that you're most excited about? What are some of the applications that you're most concerned about?
Yeah, David, you touched upon a couple of themes, and one of the themes, and I'll just touch on it really quickly, and then move on to applications, is how people think about computers and how people think about data centers. For the vast majority of the last 30 years or so, people thought of data centers as a place where you store files and where you might be able to might do some computing. But I feel that long term, it is very likely that almost every company will learn how to use generative AI, how to harness this capability, and produce intelligence. And what I mean by that is, if you abstract out what NVIDIA does for a living, there are all these electronics and software that sits inside a data center. You apply electricity to it, and tokens come out. And so if you simply reduce the problem that we do with raw data that comes in and in valued tokens that comes out, we're really a intelligence manufacturing system. It's no different than water goes in, steam comes out. Water goes in, electricity comes out. You apply fire. Oil goes in, crude goes in, and refined gasoline comes out. And so in the future, you're going to have data that goes into a building, and that building is going to do basically one thing. And it's going to work all day, all night, and it's going to produce intelligence that we apply, in certain amounts to almost every application that we do. The applications that we originally saw were related to perception of all kinds, radar perception, camera perception, microphone perception, sonic perception, all kinds of different types of perception capabilities. So speech recognition became possible, computer vision became possible, and it started off a whole bunch of industrial revolutions in autonomous driving, of course, in robotics, of course, surgical robots, all kinds of interesting applications, and it moved entire industries. We're now at a place where the type of applications are really quite extraordinary, and the reason for that is because we made a breakthrough. The industry made a breakthrough in language understanding, and it's just not language of humans. We created that language, but it's the language of just about everything that has structure, and of course, a lot of things have structure. Otherwise, the world would be white noise. And so we now recognize the structure of chemicals. We recognize the structure of genes and proteins and structures of proteins and leading to enzymes and molecules and cells eventually. We'll be able to understand the structure of a whole bunch of different biologics that I think is going to be really exciting. And so the area that we're doing a lot of work and I'm really excited about is generative AI for understanding the language of biology. And we see a whole bunch of exciting startups that are doing work in this area. Scientia, they're engineering antibiotics, Evozyme. They're engineering enzymes, biological catalysts for all kinds of different applications. It could be for consumer goods. It could be for combating climate change with enzymes that could help to absorb carbon, industrial applications, agriculture applications. So the ability for humans now to be able to engineer proteins, not just engineering chips, not just engineering software, but engineering proteins, has such extraordinary opportunities. And maybe in a larger sense, AI for biology, but AI for science. The thing that's really cool about a universal function approximator is it might not allow you to understand causality, but in many fields of science, we understand the Maxwell's equations. We understand thermodynamics. We understand how things conduct. We understand the basic science, and we've understood it for a very long time. But we've never been able to do it at a sufficient scale because the principled mathematics of the science is too computationally intensive. And so, for the very first time, we could use AI with the purpose of not trying to understand the basic science, but to scale up the systems so that we can emulate extraordinarily large systems. And one of the areas where we're trying to model the large system is the entire climate of the Earth. And we call it Earth 2. And we've successfully now demonstrated that we can accelerate weather prediction and climate physics prediction by about 100,000 times. And so there's a belief system that AI takes a lot of energy. In fact, it's exactly the opposite. AI is supremely energy efficient. Now, the reason for that is because a few people train the language models, a few people train the models, but many can operate the models. And when you operate the models, you save an enormous amount of energy. And the reason for that is because you do it so efficiently in predicting the output. You're not going through a whole lot of principled mathematics, you're just predicting the output. And so in the case of our climate simulation system or emulation system, not a simulation, but an emulation system, we're able to predict weather and climate so effectively that the amount of energy we use is dramatically reduced. And so this is an area that I think a lot of people misunderstand about AI, and I hope that there's a lot deeper understanding of this area where we realize that pushing forward into AI is the best way for us to reduce the energy consumed of computing and for a whole bunch of other things. And so, anyways, I'm excited about AI for science. I'm excited about AI for biology.
That's really cool. Let's pull on that thread of applications for a little bit, but take it in a slightly different direction. Given NVIDIA's roots in gaming and computer graphics, how do you foresee the evolution of virtual and augmented realities impacting not just entertainment, but other sectors like education, training, manufacturing? And how is NVIDIA preparing for this kind of blended reality future?
We're working a lot in the whole area of virtual reality. And virtual reality, let me just redefine virtual reality as using a computer to recreate what otherwise is physically based and real. I don't mean just putting on glasses, I just mean the computation of it. Virtual reality will be essential for the next generation of AI. And the reason for that is because there are many forms of AI that interact with the physical world, robotics, for example, or AI that has to be grounded in the knowledge of physics. For example, AI for biology. It has to be grounded in an understanding of biology. And in order for an AI to be grounded in physics, you have to simulate in physics. This is no different than airplane pilots who learn how to fly a plane or stay sharp about their flying skills by sitting in flight simulators. In the future, AIs will have to sit in simulators. And in those simulators, they'll learn how to perform their tasks, they'll refine their skill, and they'll give us the opportunity to change the loss function, change the reward function, so that the robot could perform new skills and be better aligned or be better adapted. And so virtual reality will be essential to the future of AI. And it's also the case that AI will be able to interact with humans through augmented reality. And in fact, we do it already today. When you interact with ChatGPT, it's an augmented reality system. It just happens to be that you're typing it into a phone, or you're talking into a phone. But obviously, ChatGPT could speak back to you right directly into a microphone in your ear, or it could generate images directly into your glasses. And so augmented reality is the way that AI, if you will, leaves the virtual world and interacts and helps us in our physical world. And virtual reality is how computers and AI could interact, so that AIs could learn how to be smarter AIs. And so I think that it was fashionable to talk about AR and VR a few years ago, but fashion or not, on first principle basis, innovators have to think about the fundamental reasons why certain technologies are essential in the future. And there's no question VR and AR are essential in the future. And every single AI will have a digital twin. And that digital twin will come into our physical world through AR. That digital twin will learn how to be an excellent AI using VR. And so the interesting, maybe an interesting thing is that computer graphics, or GPUs, enabled modern AI. And then the next thing that happened was AI helped NVIDIA reinvent computer graphics. The last 5 years, we've used AI to completely reinvent computer graphics. And now we're going to use computer graphics, this reinvented way of doing computer graphics, to help AI reach the next level. And so I'm glad you asked that question. That the computer graphics, GPUs, AIs, they're all really intertwined.
It's the innovation that begets more innovation.
Yeah, that's exactly right.
So we've talked about your vision. We've talked about how that's changed. We've talked about hardware. We've talked about applications. We've talked about software. Now, none of this works without people. And you've said before that hiring the right people is 99% of a CEO's job. How do you think about talent and innovation, as well as workforce development and immigration, in the context of the tech industry today?
The fundamental job of a CEO is to create the engine of creating the products that they sell. And the engine of our company is the workforce and the way that they work together. And it's a tricky thing to go do, because in order to have an innovation engine, you need talent, but talent won't come unless there's a sense of purpose. And that sense of purpose can't be realized and can't be activated without a platform that translates all of that talent into something useful. And so this talent purpose platform, this soup, if you will, is the classic chicken and egg problem of a company. And I've been lucky that I've been CEO for almost 31 years now. And I remember the first few people that I hired, and I recruited talent this morning. And what I do for a living is to create the conditions by which amazing people could do their life's work. And this engine of talent, purpose, and innovation platform for every CEO is a great challenge. And there's no easy answers to it, aside from the talent will only come if the quality of work is good. The talent and the quality of work can only turn into value if the innovation platform is useful. Now, the one area that I would say is that increasingly the vast majority of our new talent, the new source of AI talent, comes from universities. And this is really quite an extraordinary thing, because the rate of progress in AI is so fast, and all of the knowledge is so modern, so fresh, that the vast majority of the talent is in universities. And so I would encourage us to be really mindful and really thoughtful about immigration so that we could train the world's talent in AI, but keep them here. We're really fortunate to be a place where people love to come work. Our attrition rate is world-class low in technology. It's only 2.5% to 3% globally. And so we're a 30,000 people company, and people love to stay and people like to come. And so I would encourage us to be really, really thoughtful about immigration. We are so fortunate to be the place where the world wants to come and educate, and we hope that they continue to feel safe to stay, that they feel welcome to stay, and that's increasingly something of concern. This is I think the source of the IP of the United States, and this is the source of our innovation engine, or the source of our talent.
Yep.
And I hope we continue to be the place where people like myself, a long time ago, I had the benefit of coming to this country, and this was the land of dreams for us. And of course, in my case, it was a dream come true. But I hope that this will be an opportunity for so many more generations to come.
I think that's absolutely right. And along those same lines, too, I know when you gave that speech at Taipei University, National Taipei University, that made the waves in the Asian community here in the United States and was an inspiration for a lot of us. So, Jensen, thank you so much for your time and sharing your thoughts with us today. Everyone, please join me in thanking Jensen Huang for this important conversation.
Thank you all. Thank you, everybody, for doing the important work that you do.